Hi, I'm Jonathan Aldrich, and this is a poster and demonstration to go with our Onward paper, a case study in language-based security building an I/O library for Wyvern. This is joint work with Jennifer Fish and Daria Meliker. In our paper, we explore three language security features: object capabilities, effects, and language extensions as libraries. Our case study builds an I/O library for Wyvern, which supports all three of these features. Our Onward paper reports on what worked, what didn't work, and some directions for future research. Here, we'll show three quick demonstrations of how these language security features could be useful based on our I/O library work. The first feature we'll look at is capabilities, which restrict the privileges of code. A capability is a reference to an object that lets you do something. In capability-based security, having a capability is the only way to accomplish a goal. For example, let's imagine we're writing a program. The main module has a capability to the file system. We want to use another module, but we don't trust it. So what we can do is create a second capability to just a single file, and then make a reader for that file and only pass the reader to the untrusted module. Now the untrusted module can only read. Let's look at how this works out in code. Here we have a program that takes two capabilities, one to the Java foreign function interface, which is kind of the Uber capability in our system, and also to standard out. We import file system as well as the untrusted module, and we instantiate file system by giving it a capability to the foreign function interface, which now means we can use the file system. We'll go ahead and create a reader, pass the reader to the untrusted code, and then print out the result. When we compile the code, it prints out, it reads conference.txt, and we find out that we're in fact in Onward 2020. Now let's look at our code. Our untrusted module is just reading. But let's say we want to do something more. For example, maybe a nefarious attacker will import the file system, instantiate it, and read the password file. What happens if they try to do this? Well, as you can see, we don't actually have a capability to the foreign function interface Java, nor do we have a capability to the file system from main, and so we fail. No variable named Java is in scope. The attacker has been thwarted. The second feature I'd like to look at is a static effect system, which can describe what different functions might do. For example, in a blogging application, save might write to the local file system, whereas post might write to the network. A function with unexpected effects might be suspicious. For example, if save is modified to write to the network, we'd like to know about this, and our effect system can alert us to this problem. Here we have save, which has a file effect, and post, which has a network effect. If we compile things, everything works as expected. However, if we go ahead and change the save function so it actually posts, well, that might be, first of all, surprising, but it might be a security risk, right? We're expect to only write something to the local file system, but we're writing something to the network here. If we compile again, we'll get an error message. And the error message actually comes because we have other code that calls save, and that code that calls save only expects to make a file have a file effect here, edit, right? It has only file effect, but that is now changed because the effective save now has a network effect. A third approach we'd like to look at is language extensions. Using languages within strings can cause problems. Examples are command injection, SQL injection, format string vulnerabilities, etc. Now, true language extensions can forestall these problems, and we can import them as libraries in Wyvern. As an example, I'll show you format strings. In Wyvern, you can't even express a format string vulnerability as you could in C. The demo will show why and how type checking helps. In this code, we first import the format string library, and we import metadata, which brings the language into our context. Now we can define a conference variable with Onward, and we can print the conference. The value of the variable gets pasted in a safe way. And notice that because we show where the pasting happens, and we give the expression right there, we can't do the C problem where we give too many format specifiers in the format string and then not enough values for it, which is the source of a format string vulnerability. We can, of course, also print integers and floating point numbers, as well as booleans, but one thing we can't print is functions, such as this ID function. As you can see, we get an error message saying that the expressions inside a format string must be of type int, string, float, or boolean. Now, if we go and fix this and we put a value in instead and recompile, then things work as expected. Hopefully, this demonstration has shown you that these language security features can be useful. Capabilities restrict the privilege of untrusted code, effects can identify suspicious changes to an application, and language extensions make certain vulnerabilities impossible. The case study in the paper describes more about what worked, what didn't, and future research based on our case study. I hope you'll read our paper and come to our talk this Tuesday or Wednesday, depending on what part of the world you're in.